Hello scientists, and welcome to Inquiry Question 1 of Module 1 of the Science Extension course. This question asks, how have philosophical arguments influenced the development of modern scientific research? So in this module, you will identify a variety of philosophical viewpoints and describe the influence that they have had on science. So philosophers have developed a variety of philosophies used to explain how we see the world. And we're going to explore the key ones that have influenced science. Epistemology is the branch of philosophy that investigates the origin, nature, methods, and limits of human knowledge. Epistemology explores the construction of concepts, the nature of conditions, and the validity of our senses. This allows for a concept of truth to be established. Essentially, epistemology is exploring what is knowledge and where does it come from. So knowledge is knowing an answer to a question. This answer will be a fact. Therefore, knowledge is a way of being connected with a fact. What we know must be true or factual, or else we don't really know it. So what do we base this knowledge on? Maybe we base it upon our senses. We know certain things because we can see and perceive them for ourselves. Maybe we base it on language or authority. We have been told it by someone who knows better than us, or we've read about it. Maybe our knowledge has come from emotion or intuition. We can feel what's the right thing to do, particularly when looking at issues of ethics. Or maybe we're applying logic and reasoning to determine what our knowledge is. If we look at the idea of navigation, this has developed over time, but all throughout different cultures, there's been ways of navigating to find their way. People have known how to find their way. But how did this knowledge come about in each culture? Early navigation was about keeping sight of the land, so it relied on our senses. They would line up landmarks such as a near rock against a distant point on land, and doing that in two directions gives more or less a precise geometric location on the surface of the sea, and so they could work out their position. The Phoenicians used the position of the sun. They knew about east and west. They spoke about Azu, the sunrise, and Ereb, the sunset, east and west, and these names remain as Azu becomes Asia and Ereb, Europe. And so this is what they used to navigate. They got the sense of direction. But at night, they had to use the stars. At any one time in the year, at any one point on the globe, the sun and stars are found above the horizon at certain fixed heights. Now, this is a distance that mariners can measure with a simple instrument such as their fingers. So they could hold out their fingers on top of the horizon and count how many fingers high these stars were. The Norsemen were too far north that stars were not very effective, particularly in the summer. And so they would watch the birds and their behaviour to determine which way they were going. The ancient Greeks moved more into the authoritative knowledge. So these first few are all about what people are perceiving. Okay, there was some knowledge passed down, but they were still perceiving it. Whereas they started to produce sailing directions, similar to maps, which compiled all the information collected from sailors and documented the key ports and the routes that they needed to travel. The ancient Polynesians navigated their canoes by the stars and other signs that came from the ocean and the sky. Navigation was a precise science, a learned art that was passed on verbally from one navigator to another for countless generations. The Arabian Kamal was a rectangular plate that one moved closer or further from one's face until the distance between the North Star and the horizon exactly corresponded to the plate's upper and lower edges. And so you can see in this picture here, the distance that the plate lay away from the face, measured by a string tied to the centre of the plate and held at the other end of the tip of the nose, determined the latitude. The astrolabe was a disc of metal that was held suspended by a small ring. The disc had a scale with degrees and a ruler for measuring the height of an astronomical body. Okay, so you can see now we're starting to move away from just our own senses, and now we're starting to use a bit of technology. The sextant was an astronomical instrument that used to determine latitude and longitude at the sea by measuring angular distances, particularly looking at the altitude of the sun, the moon, and the stars. And then we move to a primitive compass. So the Chinese knew about magnetism as early as the 3rd millennium BC, and they produced a device that would rotate and always point south. So our current compasses point north, but they had south. So you can see here this little spoon-shaped thing that would roll around until it was pointing south. And then we have the compass that we know today, which was first mentioned in 1187 in the Common Era, and this is the magnetic needle that points north. So we can see through exploring all of these different navigation systems the way that knowledge has developed in similar or different ways, and how different cultures have put priority on different ways of knowing. But science distinguishes itself from other ways of knowing and from other bodies of knowledge through the use of empirical standards, logical arguments, and skepticism, as scientists strive for certainty of their proposed explanation. If we think back to that ballerina where there wasn't a real answer, that's not scientific. Science wants to understand, and actually there's a link on that slide if you want to go back. You can actually read the science behind what's happening there. So, the key thing we think about when we talk about science is observations and what we can see. This is empiricism. This is the theory that all knowledge is based on experience derived from our senses. Galileo's first trial of strength with the university professors was connected with his research into the laws of motion as illustrated by falling bodies. It was an accepted axiom, that is, a statement which is regarded as being established, accepted, or self-evidently true, of Aristotle, that the speed of falling bodies was regulated by their respective weights. Thus, a stone weighing 2 pounds would fall twice as quick as one weighing only a single pound, and so on. So at the time, this was just accepted. It made logical sense, but no one had actually tested it. No one seemed to have questioned the correctness of this rule until Galileo gave his denial. He declared that the weight had nothing to do with the matter, and that two bodies of unequal weight would reach the ground at the same moment. As Galileo's statement was flouted by the body of professors, he determined to put it to the public test. So he invited the whole university to witness the experiment which he was about to perform from the Leaning Tower of Pisa. On the morning of the day fixed, Galileo, in the presence of the assembled university and townsfolk, mounted to the top of the tower, carrying with him 2 balls, one weighing 100 pounds and the other weighing 1 pound. Balancing the balls carefully on the edge of the parapet, he rolled them over together. They were seen to fall evenly, and the next instant, with a loud clang, they struck the ground together. The old tradition was false, and modern science, in the person of this young discoverer, had vindicated her position. So this shows you how early on Galileo used science. He got people to experience what he believed to be true, and when they all saw it for themselves, it was accepted. In science, we also talk about falsifiability. Falsifiability is the capacity of a statement, theory, or hypothesis to be contradicted by evidence. Now, in science, we actually look to disprove rather than prove. The idea is that we come up with our hypothesis and then we try to disprove it. So we develop what's called a null hypothesis. So our hypothesis, as we know, is an educated guess based on observation, and usually our hypothesis can be supported or refuted through experimentation or more observation. But if we generate a null hypothesis, this is a general statement or the default position that there is no relationship between two measured phenomena or no association among groups. And so we can disprove our null hypothesis, and thus this would support our hypothesis. For example, if I hypothesized that the sun would rise every single day, but how would I prove that? I would need to look back in history every single day and make sure that it has always risen. I would then also need to look into the future. And even then, if I looked 100 years in advance and it rises, does that mean it will? What about on day 101? Okay, I can always keep going, and it's very hard to prove. However, if I tried to disprove it, I'd only need one instance where it hasn't happened, and that would disprove that the sun always rises. Now, of course, this isn't possible, but you get the idea. Another form of reasoning is inductive and deductive. Okay? And these are both used in science in different ways. Inductive reasoning is a type of logical thinking that involves forming generalizations based on specific instances that you've experienced, observations you've made, or facts that you know to be true. So you start with your observations, your inferences, you look at patterns, you formulate your hypothesis, and then you develop your own theory. That's inductive reasoning. Deductive reasoning is the process of reasoning from one or more statements or premises to reach a logically certain conclusion. So here you start with the theory, generate your hypothesis, and then make observations to confirm your hypothesis. So deductive reasoning goes from those general principles to a special case, whereas inductive reasoning goes from the specific instance to the general principle. So let's have a look at an example of inductive reasoning. In a very dark chamber, at a round hole about 1/3 part of an inch broad, made in the shut of a window, I placed a glass prism, whereby the beam of sun's light which came in that hole might be refracted upwards towards the opposite wall of the chamber, and there form a coloured image of the sun. These are the words that Newton wrote in his paper in 1704. Isaac Newton devoted considerable attention to the question of just what he could justifiably infer from his observations, and the assumptions that would be required to justify those inferences. After a series of further experiments and observations, Newton concluded that the light was made up of different rays which refracted differing amounts. Furthermore, he used this knowledge of the light from the sun to attribute the limited resolution of telescopes to the same refraction occurring in the light of the stars. So he made his observation, developed his hypothesis, tested it, drew some conclusions, and developed his scientific theory. Here we can see the process of induction in action. Induction inferences consist of a simple generalization from observations made in some finite sample to some broader population. Newton assumed that the light from the sun behaves the same on all days of all years, in all locations, or that the light from the stars would behave in the same way. But none of these assumptions were justified. How do we as scientists justify all the assumptions made when we draw conclusions from inductive reasoning? So we need to be careful that inductive reasoning makes sense. Okay? In this instance for Newton, it did. Okay? It turned out that the sun does behave the same way on all days in all locations. But these are things we could test and have since been tested. People have checked, did Newton's ideas hold up? Deductive reasoning, on the other hand, draws general principles from specific instances. It draws specific conclusions from broader ideas. A premise is a previous statement or proposition from which another is inferred or followed as a conclusion. Unlike inductive reasoning, which always involves uncertainty, the conclusion from the inductive inference are certain provided the premise on which they are based are true. Scientists use inductive reasoning to formulate hypotheses and theories, and deductive reasoning when applying them to specific situations. So let's have a look at some examples. In physics, we have electric circuits. Our first premise is that the current in an electrical circuit is directly proportional to the voltage and inversely proportional to the resistance. That is, I equals V over R. Our second premise is that the resistance in a circuit is doubled. Now, if both of these premises are true, therefore it follows that the current in this circuit is cut in half. Let's have a look at a chemistry example. The first premise, that noble gases are all stable. The second premise, neon is a noble gas. Therefore, using these two premises, I can conclude that neon is a stable gas. And for the biologist, my first premise, monocot flower parts occur in multiples of 3. Second premise is that apple flowers have 5 petals. So if both of these premises are true, then apple trees must not be monocots. I hope you can see the way that deductive reasoning applies these logical steps. Have a go at the quiz that's in the PowerPoint to see if you've really understood this idea. Let's take a look at another one. Occam's razor, also known as parsimony. This is the principle that in explaining a thing, no more assumptions should be made than necessary. It suggests that the simplest explanation is the most likely. For example, in medicine, one should assume a single cause for multiple symptoms, rather than multiple causes for each of those symptoms. The principle of parsimony, which we also refer to as Occam's razor, is a fundamental aspect of science, yet it's often overlooked. In short, the principle of parsimony is one of simplicity. We should not go looking for more complex explanations when a simple one will do. What that really means in practice is we should go with the weight of the evidence available to us. When there is good evidence to support one idea and only slightly less good evidence to support another, how do you choose between them? We must take the first. Philosophically, if we can choose a slightly less good answer, then why stop there? Why not take any explanation you like? Within evolutionary tree building, parsimony indicates that all other things being equal, the best hypothesis is the one that requires the fewest evolutionary changes. It makes sense that for evolution to occur, it's going to occur in the most simple way. For example, if we compare these two trees below about vertebrate relationships using the parsimony principle, then we can see that hypothesis 1 requires 6 evolutionary changes and hypothesis 2 requires 7 evolutionary changes, with a bony skeleton evolving independently twice. Although both fit the available data, the parsimony principle says that hypothesis 1 is better, since it does not hypothesize unnecessarily complicated changes. So, are there any problems with parsimony then? Well, parsimony is meant to guide you towards the most reasonable explanation for a phenomena based on what you know, but not necessarily towards the one that is right. We must also be careful not to oversimplify an explanation to a point that it no longer explains the data. So if we look at this example below using the graphs, we can see if we join every dot, this is really trying to explain every little detail in this graph. So this is a non-parsimonious fit. If we do what we would know as a proper curve of best fit, okay, then we can see that that is a simple explanation that explains why we find that data where we do. However, if we oversimplify this line and turn it into a nice simple straight line, we can see that it actually no longer explains the data. Confirmation bias is the tendency to seek out and assign more weight to evidence that confirms a hypothesis, and ignore or underweigh evidence that could disconfirm the hypothesis. As such, it can be thought of as a form of selection bias in collecting evidence. This little image here shows it nicely. Often we have our own little circle of beliefs, and there's a whole bunch of facts. But what we focus on and what we pay attention to are those facts that fall within our circle of belief. Theory dependence of observation is where observations are theory dependent, that is, they are linked to theory. So this occurs if their generation, their content, or their scientific acceptance depends in any way on the supposition, perhaps implicit, of some theory. For example, by interpreting a finding by using a theory to calculate the result, or by assessing the conditions of observations as favourable. If the framework in which observations are reported presupposes that a theory is true, then it seems that those observation statements cannot be impartial tests of that theory. It's a type of confirmation bias. Now let's just explore one more component, that is cultural observational knowledge. And for us, we're going to look at the Indigenous culture. Just one generation ago, Australian school students were taught that Aboriginal people couldn't count beyond 5, wandered the desert scavenging for food, had no civilization, couldn't navigate, and peacefully acquiesced when Western civilization rescued them in 1788. However, none of this is true. Aboriginal Australians were the world's first scientists and astronomers. They had sophisticated number systems, used natural medicines from the bush, navigated the stars using complex maps, and were able to understand the link between the moon and the changing tides. So how was it not known sooner that Aboriginal Australians were such good scientists? Well, everyone is fallible. We grow up in a paradigm, such as Aboriginal culture is primitive, which we accept as true. Anything that doesn't fit into the paradigm is dismissed as irrelevant. Ideas change slowly, as scientists allow their theories to influence their observations. We must overcome the intellectual inertia that keeps us in that old paradigm, stopping us from recognizing the enormous contribution that Aboriginal culture can make to our understanding of the world, and to our attempts to manage it. In recent years, it has become clear that traditional Aboriginal people know a great deal about science. They knew and understood the complex movements of the stars, the sun, the moon, and the planets. I hope you've enjoyed this module. It's quite a great way to look at science by starting with the philosophy of what is knowledge and how do we know anything.